My name is Heike. I'm also a new professor here, and it's my great pleasure to introduce the speaker today, Heike Vallery. So I'll talk about her in a second, just to revise a little bit the program for today. We have a couple of events and an announcement. As you know, so this posted session on the other side of the floor, some of you have been there. So the posted session is going to be running for an hour after the talk finished. So you're all invited to get a glimpse of the research done by our PhD students. The announcement is that this is the last colloquium talk before the AI week. Okay, so write down your calendars. So for the last week of September, from September 25th to September 29th, plenty of exciting activities around this AI and AI here at the university. So hope to see you over there. Okay, and today, so we have Heike Vallery. So Heike is a new professor, Alexander Commando professor that started a few months ago at the university. April, if I recall it correctly. Actually, is coming back to her alma mater. She studied mechanical engineering here and finished some years ago. And after that, she went to do a PhD in robotic assisted rehabilitation, a topic that is very connected to what I'm talking today at the Technical University of Munich. Since then, she has been in many places, including some places that she's still affiliated by like the Technical University in Delft. Okay, as we are all aware, so big changes and big successes in AI in the last few years. Most of this success have to do with simulated or virtual world. Today, what I will talk about is actually the use of machine learning data-driven techniques in the real world. In the real world, okay, interacted with real people, what sometimes associated with the idea of embodied AI, but with a number of very interesting and difficult challenges. Okay, so we'll be talking about that, and I don't want to take more of the time. So, thank you.
Thank you very much, Hector, for these very kind words. Yes, so actually I was surprised when people started calling an AI person, because I build robots and I control them, and sometimes I use AI techniques for this. So I try to make a presentation that you will find interesting, because I will try not to give solutions. You saw many algorithmic solutions in past seminars, but to try and give some challenges and opportunities that I think are still there and unexplored when trying to bring AI to the real world. So robots that I have been involved in here, you see is a selection of these, some in Zurich, some in Delft. And well, all of these devices have in common that mostly they walk, or they help people walk, or at least move. And when I started, I was a pure control engineer. I did my PhD in control engineering, looking at a general control concept. You have a plant, some sort of differential equations that you want to control in some way, that the controller that manipulates those differential equations to give the desired behavior. And that's basically how I approached the whole question. And of course, there's many things that can go wrong. If you look at the world like this, there's a plant, and you force it to have some other behavior than what it naturally wants to have. Well, one of the things, of course, that can go wrong is that the plant doesn't follow the assumptions that you made about it, in particular, the modeling assumptions that you made. And then if you use conventional control design, then many of the algorithms reach their limits. Once you don't have an accurate model of the plant, then you're left alone. But that's where learning, of course, can come in very well. And I'll give some examples of how we combine this. So here, for example, is a system that has, you could say, very unfortunate dynamics, but that's because of the constraints that it has. This is the rehabilitation robot supposed to move a person's leg, but the person at that same point is in an MRI machine, which means that you have to be extremely careful not to have any ferromagnetic materials close to that machine. Still, we want to actuate the person. We actually have pneumatic actuators here, and we wanted to be able to control the valves, control the actuators, move the pistons while the person is in the MRI. And there would have been no way for us to do this with the entire robot close to the MRI. So what we did was we had the passive parts of the robot in the MRI, and then 7-meter long cables to another room adjacent. And these cables were not electrical cables, but pneumatic cables. So air had to flow these 7 meters back and forth. You can imagine what that means. If you ever had control theory, you know how bad things like delays are. And we definitely have a lot of delay here due to these, unfortunate configuration, but we didn't find a better solution. And I think, well, it worked okay for the purposes that we wanted, but we definitely had a problem with these delays. And here's what we did. We basically exploited the fact that here we have a rhythmic movement. At least if you just enforce a certain rhythmic pattern on the person's legs, you know when the cycle starts and ends, which means that over the course of one cycle, you can observe the errors that you make and try to compensate them, learn from cycle to cycle, which is the principle that's used in iterative learning control. So this is quite a nice principle because it doesn't jeopardize stability of your control loop. It's just an additional feed-forward portion that you use each single time that your cycle runs. And you can see here what happens. We have the reference, and we have a delayed behavior of the system where we have only feedback control. And with iterative learning control, we're able to anticipate the movement basically by learning the errors from cycle to cycle and track this reference again. So this seems like a very nice way that learning can help improve system behavior in a way that you don't necessarily jeopardize stability. Here's another example where we use learning to complement a model-based controller. This was a collaborative project together with Heidelberg, and they had developed very powerful and fast nonlinear model predictive controllers. But if you know nonlinear model predictive control, it's already in the name. You need a model. And this model will normally not coincide with the actual physical world, as is the case here. So Manuel, the PhD student in Heidelberg, he had developed these nice algorithms and he was training them on a model of our robot, or basically he developed them on the model of the robot. But then on the real robot, the NMPC couldn't do it exactly, of course, because the model wasn't correct. And then Ivan Pawlikowski, he was the PhD student on the Delft side. He was investigating reinforcement learning. And the two PhD students joined forces, and we managed to make the reinforcement learning controller only compensate for this modeling mismatch. So we could still use the benefits of the NMPC controller while also using the benefits of reinforcement learning and being able to adjust to the actual robot without having to do any complicated system ID, and also being able, of course, to adjust to constantly changing behaviors. Now, in this case, you still need a pretty good model of the robot because otherwise the NMPC controller wouldn't work. In many cases, you don't have such a good model of the robot and its environment. So we're also looking at model-free learning. Here's an example where Leo learns to walk without any prior knowledge. So he's basically just learning the relations between the actions that it takes in terms of motor voltages and the results. And then when it falls, of course, we have a high cost and it will try to avoid that next time. But what you can very well see here is that, of course, there's a problem when the robot falls. What you cannot see so well is that there's also a problem when you just try to explore. Because what these algorithms tend to do, to use epsilon greedy methods, they will just tend to introduce a lot of noise into your motors. And then if you have gearboxes, they don't like this so much. They will suffer from fatigue and eventually fail. So actually we had whole boxes of servo motors for this robot because we needed to constantly replace them. So this actually became a measure. So the robustness, the number of motors that we were using became a measure of how good the algorithms were. And then, of course, Ivan had some good ideas and some other students on what we could do, for example, not change the control signals so much. But yeah, there's also a trade-off between exploration and the number of faults that you get if you don't explore enough. So this is definitely a challenge, exploration-induced damage. And I think people might not even be aware of this risk because in simulations, you don't see. You see the faults, but you don't see the gearbox damage. I'll come to another challenge that is even bigger if you're not using such toy systems, but once you start looking at systems that are safety critical. And particularly if you try to build robots that help people walk. And here's an example of a system that Mark Bolliger desired to have for his paraplegics research lab in Zurich. And what he wanted is a system that would be able to catch a person to provide body weight support whenever they needed it. So, for example, to train after a spinal cord injury or after a stroke. And at that point in time, I had already built a robot together with Grégoire Courtine, who's a neurobiologist, and a very clever master student, Urs Keller. And we had designed this robot that would be able to guide rats or other rodents later during rehabilitation training. This is now a rat that is healthy, but of course, Grégoire was interested in how rats would recover after a spinal cord injury. And what you can see is that this robot just follows the rat, and the rat isn't really aware that there is a robot. It's really, really transparent. So we thought something like this probably also solve the question that Mark had for humans. But obviously, we could imagine that scaling this up to human size would be extremely hazardous. So we didn't do that, but instead built a completely different system with hardly any mass. And this is the result, basically just moving cables connected to a person and 4 strong motors that actuate these cables. And then there's a little zoom into two elements. One is passively displacing deflection units. So they displace because the cables exert forces on them, so they are implicitly moved. These are basically passive dynamics, movement that is not actively controlled. And then we have the series electric elements, which are basically just springs that decouple motor inertia from the person. So this is the hardware setup. And here you see it being controlled. This is all model-based control, actually. So you see here how the system can follow a person in a room and catch a person when they fall. And of course, it can also apply forces in all directions. So you can also challenge a person if you like. And what it was also used for, then again by Grégoire Courtine, was to try and help people after a spinal cord injury recover. So we had already advanced to trying his principles of spinal cord stimulation on humans, and you can see that, there's quite some success in performing this locomotion task, but you can also see that this very much depends on how the robot is acting. So in the 3 cases, you see the biggest effect actually of the horizontal forces. So how much the robot is pulling the person forward. It makes a big difference on how fast the person can do it. So we already realized here, horizontal forces are quite important. But we also looked at the errors that we had in vertical direction. So the unloading direction where we would supply body weight support. And what we realized is, while the person moves, there's always a slight up and down movement. You constantly move your center of mass up and down, which means also the robot has to move up and down, which means since the controller is never perfect, you have this oscillatory motion in the force. Although we had wanted to have a constant force around 300 newtons, we got this oscillating force. And well, theoretically, you could do something similar as what we did with the pneumatic stepper and try to do iterative learning control. Problem here is that the person is dictating the cycle. So they are the ones who determine when the cycle starts and ends. And that makes it a lot more difficult to use this type of repetitive algorithm. So instead, what we tried was we joined forces with Renaud Rance at the Université Catholique de Louvain. And he was investigating adaptive oscillators. So networks of oscillators that can synchronize to some inputs. And in this case, we try to basically learn the rhythmic up and down movement of the person. And if that is sufficiently periodic, then you can get a perfect fit of your oscillator. And once you have this, you have predictive power. You know what will happen in the next millisecond, in the next 10 milliseconds. And you can use this to actually already guide the motors to that position and thereby avoid all oscillations and force. So this seemed like a great idea, but something we had completely neglected was thinking before, what is actually the real cost function or reward here? And we had made the implicit assumption that we want at constant force. Seems reasonable because Gravity is a constant. You take away part of gravity, so you should take part of a constant away, also a constant. But that's an assumption that makes life a lot more difficult. We had to implement this entire controller that would learn how to get rid of these oscillations. So we took a step back and asked us, is this assumption actually correct? It's actually a prevalent assumption, and it sounds very intuitive, but it makes life so complicated that it's worth questioning it. So we did a simulation study, or rather, the clever master student again, Salil Apte, did this simulation, and he compared 3 conventional concepts of body weight support against each other. One being the constant force, which we thought was the perfect situation. One being a counterweight. We already anticipated this is probably not a good situation because you have just double the inertia if you do the entire unloading, but you have more inertia than you normally have. That's probably not a good idea. And then you have the spring. Probably also not a good idea because you will have this position varying force, right? So idea was probably the constant force is the best. Well, at that point in time, we already kind of suspected that it might not be the best, but we went into this open for any result. And what we measured was in the simulation study was the dynamic similarity of gait. So how natural would people walk despite the fact that they were being unloaded? Of course, we want them to train walking in daily life in this system. And although we have to give them some body weight support to make them be able to walk, we still want them to do the same walking that they would do without body weight. So that's why we looked at how similar the gait pattern would be without the support. And what we saw, or you can already see it in this picture, is that indeed the counterweight is not a good idea. It doesn't help the similarity. And if you do more and more body weight unloading, you get less and less similar to normal gait. But what definitely is a surprising result to the field is that the spring actually outperforms the constant force. You're more similar to natural gait than if you provide a constant force. Well, of course, we have some hypotheses about this, and you can also intuitively think about it. What happens if you take away gravity? You take away part of gravity, but you leave all of the body's inertia. Basically like walking on the moon. You have less gravity, but your inertia is still there. So you will start moving a lot slower. Your eigenfrequency will go down. So dynamic similarity is less good. If we insert a spring, what we basically do is we increase the eigenfrequency again to the point that you would have without the unloading. So that's the hypothesis that we had. And actually it was, it was confirmed in this simulation. So that's, I think, one of the first warnings. What's the reward function is often the biggest question to ask. And often there's a seemingly intuitive or logical assumption, and it might not actually be correct. So question assumptions, especially if they make the design more complicated. So if you can get away with a simpler design by questioning this assumption, it's a good moment to actually check it, whether it's correct. Okay, now having found out that having a springy behavior is a good idea, we redesigned the entire cable robot, and it became a new robot called Levitation, and it has these passive huge springs over here. And basically they are the first line of defense against any movement of the person. And we really can very much scale down the power that we install in the motors responsible for the vertical motion, which means we save a lot of energy and simultaneously probably make walking better, more natural. And something I don't want to hide is this very interesting winch here, which is a strangely shaped winch. It's basically like a cam. What we do is we compensate the non-linearity of the kinematics of the robot with this mechanical compensator, you can see. So the person moves left and right, and this winch moves left and right, just kinematically coupled. In the simulation, you can see it even better. And what you see is that while the person moves, the radius of the winch changes for each side. So if, for example, the green cable is short, so you're on this side of the room, then you have a larger force in the green cable than in the red cable. And this large force on the green cable meets a small radius. See that? While the smaller force on the red cable meets a larger radius. If you're a mechanical engineer, you know moment equals force times lever arm. And in this case, we calculated it such that the lever arm would exactly compensate for the kinematic nonlinearity, and thereby we would have zero moment on this winch. which of course means that you don't really need a motor for the winch unless you want to compensate for friction, for example, or generate some sort of perturbation or assistance in this direction. So again, an effort to save power. And here's the resulting robot. It basically does the same as the robot that you saw before, but now it's so low power that you can plug it into the socket on the wall. So it's a extremely low power system, and that also makes it a lot safer. I'm putting this into the AI colloquium because I think it's important for people to realize that if you did this algorithmically, you wouldn't get the advantages of saving all this energy. So thinking that you can solve with algorithms any shortcomings of mechanics is not a good idea. Always consider that there might be a solution in the mechanical space, and potentially you can find a good algorithm, maybe even translate it back to a mechanical design, right? Like the strange shape of the winch. So I think there's a large realm of opportunities in the domain of co-evolution of software and hardware. This was mostly hand done, but you can imagine that something like this should also be possible with AI. Okay, here's a little example of how the Ryzen robot is used. You see a child training in Affelton Albis, and you see how creative the therapists can get in the tasks that they give to the child, and how creative the child can get, and how we can explore the opportunities that he now has and play. So one of the things that I learned definitely is to look into how can we leverage human motor control? How can we not just see a person as a disturbance to a system or to a controller, but as an essential integral part of the system? And I'll come to the second opportunity, leveraging human motor control. I'll do this on the example of the gyro backpack system. Here's a system that contains fast spinning wheels. And these fast spinning wheels are rotated about another gimbal axis, which generates huge gyroscopic effects perpendicular to the first two axes. You can add these vectors up and get a rotation effect on your body. So basically, this can increase or decrease the angular momentum that your body has by exchanging it with the wheels. It basically feels like a force. It's not really a force, it's a couple of forces coming from nothing. This is also something that has been used a lot in space. So of course, we also use the control algorithms from space for the low-level control, which basically generates the torques. And here you see what those control algorithms would do when they encounter the so-called singularity, which is the unavoidable moment when the gimbal has rotated so far that the reference torque and the actual torque it can generate are orthogonal to each other, which means you cannot generate any more torque above the axis that you want. And then conventional algorithms would start oscillating. In space, that's not really a problem because you have perfect models. You can really pre-plan your mission, and you can just avoid ever getting into these singularities in many cases. In our case, we cannot avoid it because we're coupled to a person, and much of the behavior of the system is determined by how the person moves. So we had to develop new controllers, and we did this using conventional control theory. So there was no learning involved here. So the low-level controller just tries to anticipate how close it is getting to the singularity, and once it's getting too close, it just won't ask any more torque. And then what happens is what you see on the right, it will just stand still, which means you suddenly have no more torque, but at least no oscillating torque. Now that we have this torque source, we can start looking at the high-level controller. How will this interact with the person? First, we just do open loop, basically generating the torque on the person. And here, this is Daniel Lemos, the PhD student, experiencing this for the first time around 2014. I really like this video because it shows the surprise at how much torque this system is actually generating, or how large the effect is that it has on his body, which also depends on when in the gait cycle it will catch him. So we're actually surprised that we see this effect because we had tried it on an inverted pendulum and it didn't look so spectacular, but it's actually pretty easy to influence people's balance with rather low torques. Now, of course, we can use this open loop system to, for example, identify human behavior. And this was done with collaborators in Darmstadt who tried to find out how human muscles respond to balance perturbations to the upper body, which is something that so far wasn't really possible to do, or at least not in this free torques form. Of course, this wasn't built to be a perturbation device. It was built to be an assistive device. We wanted to have it help people with their balance. And here's some experiments that we had set up that we wanted to do in Delft and in Chicago, where our partners were at the Shirley Ryan Ability Lab, at that point still called the Rehabilitation Institute of Chicago. And we just tried to expose people to challenging situations and find out whether they could balance better, for example, walk along a beam or stand on a narrow support surface. Here you see a person trying to walk as far as possible on a narrow beam. And as soon as the person steps down, we measure the distance they walk. And in the left condition, there's just the person with the safety harness. In the middle, the person is wearing the device, but it's switched off. So with dead weight, and on the right, the device is assisting balance. And now you can see in this video, but it's consistent across trials and across people, that it's a lot easier to walk with assistance. Now you might ask, what is the system actually doing here? What's the high-level controller? And the high-level controller is actually very, very, very simple. We had tried quite sophisticated controllers, and then we tried a couple of simple controllers, which are basically just PD controllers, proportional derivative, or a spring and a damper. Meaning you could upright the person to a perfect upright position, or you could just damp all their rotational movements. And then we did combinations of these, just the spring, just the damper on the spring damper. And of course, we thought probably the spring damper is going to be the best. It's going to help people stay upright. But we were very much surprised that this was actually not the case. The best controller was the pure damper. So we gave no reference to the person what the posture should actually be, because the damper doesn't need an absolute reference. We only absorbed energy from their body. That's all. And thereby we gave people again the possibility to control themselves, how they balanced. And this worked best. So we just slightly manipulated human dynamics. We did not override them at all. So this was quite interesting. I think it probably holds true for many other more general questions, how you should design controllers that interact with humans. My personal conviction is you should try and deliver a sort of environment to a person that facilitates their motor control, but doesn't override it and tries to make use as much as possible of their motor control. Now, here's an example of how the controller and the device worked for a stroke survivor. This is in Chicago in our Room Jayarman's lab. And we again have the same three conditions, but the slightly different task. The person is asked to stand as long as possible on this beam. And what you can see is in the first two conditions, it's very, very difficult. And the person has to step off very quickly. While on the right, the person can stand for a very, very, very long time. And you can also imagine that this might have to do with the very fast movements that she exhibited in the first two conditions, and the device just taking some energy out of that movement and allowing her to concentrate better and have the slower dynamics, basically. Now, this was also quite consistent. In that experiment, we had 5 stroke survivors and 5 healthy subjects, so still only a very small group of people, and we need to do more experiments, or we're actually in the course of doing more experiments. But at this point, what I can show you is that all of these 10 people, healthy subjects and stroke survivors, all of them improved their balance. And remember, this is an extremely simple controller, just a damper. It's not doing anything else. Okay, we spent a lot of time building these prototypes. Actually, the hardware design cost us much more time than the software design. You see here multiple generations, and in the end, we came to a really small device that you can now put into about 5 kilogram backpack, down from the 16 kilograms that we had before, which was impractical. So we're slowly coming towards something that we can use. And now we can also look again at the controller and try and, for example, have learning controllers that adapt to a person and explore this further. But this is future work. I'll come to another challenge related to balance, which is if you want to generate this learning behavior, then you also need to have data, right? You need to have lots of data of people balancing, or ideally even losing their balance. And that's not very easy to generate. Here you see 2 of my PhD students in Delft trying to generate falls. Of course, this is not something that you can do a lot, and especially you cannot do with the target group that you actually built any of this technology for, right? So this is one of the challenges, but we are slowly getting there because this is actually part of the project together with the company Volk, who make airbags for pedestrians. So basically, these are airbags that are based on IMUs worn around the waist. And then we can detect actually, these are mostly model-based, but we have some data-driven algorithms now that detect when you are falling, and then just in time will inflate this airbag. So this is the last resort, you could say. And it, of course, has to be extremely fast because you still need time to inflate the airbag. Well, this has worked pretty well. There's now about 1,000 people who use Volk every day, and it's about 6 falls per day. So this is really being adopted in the Netherlands, and so far mostly in nursing homes, but they are now slowly expanding. It's a company that's expanding into the direction of, also individuals and potentially other countries. But this is a very encouraging project for us, and we were looking at how can we generate more data? How can we leverage the benefits of data-driven learning? And well, this is an experiment that's being done in the US, and you can see from the gear that they are wearing that this is a US environment. And Arun Jayaraman is asking healthy subjects and stroke survivors to do these falls. And then with this data, we can hopefully find better models. And simultaneously, there's now already many of these Volks actually in the field, people wearing them daily. So there's now real data of real falls, accidental falls being recorded that we can also use in the future. Okay, now I'll give a small outlook and what we're working on right now, which is minimalistic rehabilitation at home. And what we're trying to look at is how can we make sure that people, when they go home, they actually do their exercises and have fun doing those exercises, and that they are able to do those exercises. So, for example, people who have low health literacy, for them can be very difficult to use complicated technical device, to use a virtual reality environment, which is often proposed for at-home rehabilitation. So what we were looking at is actually something that the industrial designers at TU Delft came up with, an extremely simple device that has no screen interface, actually an exercise device that doubles as a sort of pet. So it's in the simple exercise device you can think of, and that's also fun to play with, is a ball. So we built, or the industrial designers built the first prototype of a ball that would somehow interact with people and motivate them to move more. And logically, the first thing that you would think of is children. So they actually started this project aiming at children with cancer, who often are in the hospital and don't move much. So they were trying to get them a little bit more active again with such an engaging toy. But in this study, they also observed that actually the adults in the room also started engaging with it. So we think that there might be also a room to use this also for adult training. And for example, for people with dementia or with stroke or other sorts of reasons to undergo rehabilitation. And well, this is, of course, something that we're working on, so I can't say much about it yet. I can just tell you that we built a new prototype that is extremely simple to use, and hopefully we can make it robust enough that it can be kicked, thrown against the wall, and really be used as an exercise device. And it's an under-actuated system. So this is just one block that's rotating about an eccentric axle. And that way we can actually make it navigate in 2D, as you can see. Even though it has just one motor, it can still do 2 directions. And if you're a mechanical engineer, you might remember that normally if you build a rotor, you try to balance it statically and dynamically, because if you don't, you get torques about strange axes, not your rotation axis. And in this case, we purposefully built a very unbalanced rotor with a non-diagonal inertia tensor, with the center of mass not on the axis, and thereby we can generate, with higher frequency movements, we can generate torques about an axis perpendicular to the axis, and with low frequency movement, we can just use the center of mass displacement to make it go in the other direction. Actually, I brought a prototype, the way I want to play with it. in the question hour. And here's a video of this prototype. Of course, this is not as appealing anymore as the industrial designers version. I hope it will become that again. So all this does currently is just try and go to one direction in space, and the person just happens to be standing there so that it looks like the device is returning to the person. But in the future, of course, we want it to actively and intelligently interact with the person, recognize what's in the room, recognize where's the person, and exhibit behavior that will entice the person to be active and engage with it. So we had a very, very preliminary workshop. So all I'm showing now is really just very preliminary. And Ada Osmonoglu, the PhD student in Delft, she designed this workshop where basically sort of hackathon, two groups competed against each other trying to program the ball. And you can program it in Python, but you can also program it in this Lego language, which is extremely simple to use. And they just had 2 hours to implement two different things. And actually, they didn't do very, very bad. I mean, well, it's just a Lego Mindstorms device in a styrofoam hull with a very simple controller. But we saw that it's actually not impossible to have some sort of consistent interpretation from people of what the device tries to say. So we commanded people to implement emotions, and you see here that at least the emotion said was quite consistently recognized. Why the emotion angry wasn't really recognized, but people very consistently thought that the device was excited. So there seems to be at least some consistency in how people perceive it. But we also made some very, for us, surprising observations, probably not surprising for psychologists, is that people started imitating each other and started interpreting behaviors just by observing other people in a different way. And also that they very creatively interpreted instructions that we gave, like hold it in your hands was interpreted by the first person by let it roll along your forearms. And then all of the other people did the same thing, which very much changed how the device behaved and how people perceived it. So the perception depended on the interaction. Quite an interesting finding for us as roboticists. Well, of course, we're trying to look into this more in collaboration with the psychologists and industrial engineers. And in the future, we'll hope to finalize a more robust physical embodiment and then learn strategies, maybe even do end-to-end learning. No emotions in the middle, just do whatever gets the person to move. Can be an interesting learning problem. Actually, and I have an open position. So if anyone's interested in this project, PhD or postdoc, please approach me. Okay, so to conclude, this is a small summary of the challenges and opportunities. This is just a selection from my own work. So don't take this as a complete list that I think would be interesting to look at when you venture with your algorithms into the real physical world. And some lessons that I learned is always question assumptions, especially if they lead to more complex design choices. And don't rely on software, not even if it's a very intelligent algorithm, to fix ill-designed hardware. Also consider the hardware. Thank you very much.
Okay, so thanks a lot, Heike, for this wonderful presentation of this fascinating body of work. Okay, very interesting things. I'm interested in the hip airbag, by the way, but we'll talk later. No, just kidding. Okay, so now we're going to open the floor for questions, comments. So for you to start thinking about a question, so I'll start with mine.